Alan Turing and his contemporaries building the world's first computers to mark the centenary of Alan Turing's birth. So this is the book, and copies will be available here. They are available here at a discounted price, specially discounted, and you can have them signed afterwards.
At no cost.
The signed ones are rarer.
And if you want to order more after that, the online BCS bookshop sells them, again with a discount for BCS members. So this is a tribute to stars, not only Tom Kilburn, Alan Turing and Maurice Wilkes, but to many other scientists and engineers who made significant contributions to early computing, 1945 to 1955. So in this seminar, the contributors to the book here are going to explain how the basic ideas for the stored program computer originated, and then they will describe how the teams at 5 UK locations built a number of prototype machines. And the talks will be followed with questions and discussions. So the seminar is going to be led by Simon Lavington, who will introduce his fellow contributors. So he will do that. And Simon is Emeritus Professor of Computer Science at the University of Essex. Among his many publications is the book Early British Computers, and also a definitive history of Elliott computers, which was published in spring last year. So I'll hand over to Simon now.
Thank you very much. Well, this is the running order for this afternoon. I shall spend no more than 20-25 minutes setting the scene and also talking about Alan Turing's particular contribution at the National Physical Laboratory, NPL. Then Martin Campbell-Kelly will come on and give the Cambridge perspective. Chris Burton will do the Manchester and Ferranti perspective, Roger Birkbeck and BTM, ICT, and then I'll wind up with an attempt to say how Turing's reputation has changed subtly over the years. In case you want to go to sleep, most of the sessions will be a quarter of an hour, so you can time your snoozes and wake up at the appropriate time. So, ideas first to set the scene. Imagine you're right back in 45, end of war, and there was talk of calculating machines of various types. I focus on the efforts in America at the Moore School of Electrical Engineering at the University of Pennsylvania, where the ENIAC computer had burst into life just about at the end of the Second World War. It was huge, it was electronic, it wasn't stored program, but it was a tour de force of engineering. And even before it had started to work, the team that was building it was looking ahead to something else, something more general, and that they called EDVAC, the Electronic Discrete Variable Automatic Computer. Discrete variable being a hint that it was a binary calculating machine. And the interesting thing is that John von Neumann took a hand in the project at that stage and wrote what has become known as the EDVAC report in June 1945. And this was quickly broadcast to various groups, mostly in the States, but in this country as well. So, although there were other ideas around, and on the top left we have a reference to Alan Turing's 1936 paper on computable numbers, and on the right we have a reference to the endeavours of Bletchley Park and Colossus. These two blocks, to the top left and top right, were not so influential in the minds of the designers of the very first practical stored program computers. The reason why Colossus was not so influential was, of course, that it was secret at that time. It wasn't until the mid-70s that the details of Colossus began to emerge to the general community. On computable numbers, a fundamental theoretical paper, Max Newman, a colleague of Turing during the war, and indeed the person who led the Colossus project, remarked when asked after the war what was the influence on computable numbers on the implementation of practical computers, and he said very slight indeed. And I think that's what I would say, except for one instance that I'll come to in a moment. So the ideas in the EDVAC report in this country were promoted by the great and good of British science because they conceived of a need for computational power for strategic purposes, and that led to encouragement to a number of groups in the UK to have a go at building practical machines. And the efforts in the green blob at the bottom is the thing that occupies most of the text of the book. So the people. At the start of the period of interest, the start of 1946, in the UK, there were precious few people who were putting their minds to some sort of practical project, and I've listed them there at 4 centres. The fifth, the Elliott Bohr and Wood Laboratory, came onto the scene a little while later. I've kind of colour-coded this diagram, and the one that's going to appear in a minute, to suggest that the names in red took a rather more mathematical, a rather more theoretical approach to the idea of a general purpose computer, whereas the names in green took a rather more engineering type of approach, although in truth practically all the people whose names will be revealed on this slide did have a mathematical training to start with. So that was at the start of things, and it should be said that at that point, at the start, there will be, hello George, I'm sure there will be ample opportunities for you and others to put your oar in later on. If I may press on for the moment, because we have a lot to get through. By the start of 1949, the groups had expanded, and indeed there was some movement. Turing, as I will say in a moment, had migrated. David Rees and Jack Good, mathematicians, ex-Bletchley mathematicians, had become detached from the Manchester group, and for all practical purposes were lost to the early days of computer design. And you can see that the names in green, if not predominate, they certainly were a big part of what was happening in the 5 groups that established themselves at the start of 1949. As for places, well, this rather complicated diagram is an attempt to knit together people, places, and the results of their endeavours. Down the right-hand margin, time is flowing, and at the bottom is the marketplace. What happened in terms of practical computers that were for sale. And what our book does is follow, basically, the red blobs. You'll see, do we have a pointer here? A sort of magic... we don't have a...
Suspect if you do it so badly, the cursor will appear.
Ah, dear, is that right? Look, yeah, oh, that was a mistake, wasn't it? Okay, change the press. Right, well, I'm going to work from the red blobs from right to left, and what we show in our book is that the prototypes, the lab-based prototypes on the right, generally speaking, had a production result, re-engineered production machine in the centre box, so that, for example, the pilot-based computer developed at the National Physical Laboratory led through the Deuce, EDSAC led through to LEO, the Lion Electronic Office, etc., etc. Manchester led through. You'll see that the Elliott stream didn't have the benefit of an academic community at its background. It had a rather interesting task to provide a classified real-time online computer for the Navy. We won't this afternoon have much time to talk about Elliott, and in any case, a year ago I bored you to death with a seminar on that subject. Nor will we have time for the block on the extreme left, which contains half a dozen classified computer projects, 3 of which were Elliott machines. These are described in the book. So, in summary, what we're going to do this afternoon is to pick some highlights for most of the red streams going down that diagram. So it falls to me to pick the NPL stream to kick off. And what I will start with is what's called the ACE report. This diagram shows the exception to the flow of ideas that I sort of hinted at earlier on. In the case of Alan Turing, clearly his early paper on computable numbers, computation of the universal machine, was of course bound to influence the way he thought about a universal computer. I think possibly of more import was the thoughts that he had bubbling away in the back of his mind during the war for what one might call intelligent machines. And of course on the right there, Alan Turing and a few others were exposed to the endeavours of Bletchley Park and the efforts of the Dollis Hill research arm of the GPO in putting some of these ideas into practice in practical electronics in rapid analytical machines, of which Colossus was one.
Can you read the black lettering on the dark blue?
Sure, yes.
More difficult.
Sorry about that. But from left to right, the top left says on computable numbers. That was the title of Alan Turing's theoretical paper. In the centre it says Turing's ideas for self-modifying code and intelligent machines. And on the right it says Bletchley and Hanslope experience. From 1943 onwards, Turing was not focused on Bletchley Park itself, but on another secret establishment, Hanslope Park, where he was engaged in the design and implementation of a speech encryption machine called Delilah. Turing took the notation of the American EDVAC report and used that notation to produce his own individual report, which is popularly known by the term ACE, Automatic Computing Engine. And that was completed at the National Physical Laboratory, to which Alan Turing moved in October 1945. He produced that a report of over 100 pages by Christmas, a significant achievement. The contents of Alan Turing's report has been studied by historians throughout the ages, really. I'd like to quote from a 1977 paper written by Brian Carpenter and others, and particularly I mentioned Brian Carpenter because he will be coming to the CCS to give a seminar in May on the ACE report and the pilot ACE. Now, Brian Carpenter, and I think most people would agree, has identified some formative ideas that are contained both within von Neumann's EDVAC report and in the ACE report. what is a little bit more speculative, but certainly Brian Carpenter can justify this, are some other ideas that touch on present-day computing, and these ideas are contained only within Turing's ACE theory. I have to say that picking out these ideas from the original 1945 report is not easy, and I've no doubt Brian will say more about this. To my mind, what the things that distinguish above others between Alan Turing's view and John von Neumann's view in that era is this generality of universal computers, and his idea that this was not just an arithmetic engine to help in engineering calculations, but had a much wider possibility. Before going on to consider what happened at NPL, it is, I think, wise to remind ourselves of Turing the man, what sort of scientist, what sort of logical, mathematical logician was he. And here's some quotes. First of all, from Professor Max Newman, who led the Colossus project, and who then, after the war, went to be Professor of Mathematics at Manchester University. Then from Mike Woodger, who joined Alan Turing in 1946 at NPL. And finally from Alan Coombs. Now, Alan was part of the group of post office engineers that implemented Colossus. And furthermore, Coombs got the job of building a post-war computer called Mosaic for radar signal analysis that was strongly based on Pilot ACE. So Alan Coombs was well placed, I think, to comment on the engineering ability of Turing. And it's worth reminding ourselves of those comments, because my next slide might be construed as seeing both Turing and the NPL hierarchy in a slightly negative light. I don't think that's the full story, but anyway, on with this slide, and you may judge. This is the chronology of events at the National Physical Laboratory between 1945 and the birth of the Pilot ACE computer, which first ran a program at May 1950. And you can see that Turing was hard at work designing and redesigning his computer right from the beginning. And indeed, by May 1946, his designs reached version 5. NPL, of course, on its staff had plenty of physicists and people up to speed in radio engineering. NPL itself did not feel at that stage that it had the capability of implementing a high-speed electronic computer. It felt, in a word, that high-speed pulse techniques were not part of the internal skill set. So between June 1946 and April of 1947, the NPL hierarchy strove to get the cooperation of other partners to implement Turing's design. These were unsuccessful. Turing made efforts to spread the word and gave a course of lectures to invitees. I should say that Jim Wilkinson, whose name appears on the second line, was to become the de facto leader of the Pilot ACE group at NPL. A person whose influence should not be underestimated. Moving down the list, Harry Husky, who had been part of the ENIAC group and was a regular engineer, so to speak, visited NPL for a week, suggested that the team get on and build something, but Alan Turing was not in agreement with this, And indeed, by March of that year, when there was an abortive attempt to set up a relevant electronics section, Turing is thought to have lost interest in the implementation of ACE. This is not to say that he's lost interest in universal computers, far from it. It is as if his mind was forging ahead and considering the implications of this idea of a universal computer. At any rate, Alan Turing asked for a sabbatical year off and spent that in Cambridge. Perhaps the most interesting result of that was a lengthy report entitled Intelligent Machinery, which was submitted to NPL but was filed away as not fit for publication. And it was only years later that the AI community discovered with delight this paper. So by April 1948, a man called Colebrook, whose first name I forget, had breathed life into the electronics section, and a combined group of mathematicians and engineers with the input from English Electric had been formed, and the implementation was well underway. But by then, Alan Turing had moved to Manchester, and Chris will say more about that later. So I'll end my section with saying a little bit about the Pilot ACE computer. And I started with the instruction format because to modern eyes this does look a trifle odd. If you look at the various fields in that 32-bit instruction, you'll see no field that is called function or opcode. Interesting. You'll see other fields that are to do with weight numbers, timing numbers, length of transfer, rather detailed, one almost might say a microprogramming level. NIS is a source of the address of the next instruction. Well, there were several machines whose instruction format included the result, the source of the next instruction. What is perhaps, George, if you, I know you're bursting because you're part of this design team. I'm sure you're going to I'm sure you're really going to blast us with the truth soon, but if you could let me rattle on for a little bit longer, I'd really be most grateful. The source and destination numbers, which we are tempted to regard as the source and destination of operands, did other things as well, and indeed were used to specify arithmetic or logic functions. I'm not going to do a complete analysis. You'll be glad to hear of Pilot ACE for two reasons. First of all, that Brian Carpenter will be talking about ACE in a couple of months' time in a CCS seminar. And secondly, because if you look on the new Our Computer Heritage site, follow the English Electric Deuce Systems Architecture indexing, you'll find a tutorial on Pilot ACE. And this is a diagram taken from that tutorial in which an attempt has been made to interpret the Pilot ACE nomenclature in terms more familiar to a modern user. And you can see I've colour-coded this diagram. Arithmetic and logic functions appear in blue, and they're distributed throughout the diagram. The purple blocks named R were in fact single word delay lines called temporary stores, and the green blocks are 32-word long delay lines. And if you look at the tutorial in the Art Computer Heritage site, you can see how the switches on this diagram are related to a more usual modern view of opcodes, etc. The computer itself, the Pilot ACE, first working in May of 1950, a most interesting machine. that was very economical with the use of hardware and fast. It's reckoned in round figures to have contained roughly a third of the electronics of the comparable other prototype store program computer projects in the UK, whilst being anything up to 5 times faster. There's a couple of things that contributed to its speed. One is its rather short digit period, a microsecond, and another, for which I need really to go back to this diagram, is its idea of capturing information at the right moment. This being a computer based on serial delay lines, you can imagine information circulating all the time in the short and long delay lines. And Turing's philosophy was that you should, for a given piece of information, whether that information was going to be interpreted as an instruction or as an operand, that you should grab it as soon as it appeared in its circulatory path. And grabbing it when you can, plus the short digit period, were the sort of things that led to the high speed. As I said, the digit period was a microsecond. The store of that and most early computers was sequential. It was the exception was the work done at Manchester and Ferranti, where the cathode ray tube electrostatic store was random access. Unfortunately, the random access memories of the time could not be driven with a digit period as small as 1 microsecond. The Ferranti Mark I had a 10 microsecond digit period. Elliott Brothers at Boreham Wood took the basic, what's called the anticipation pulse form of the CRT, and because they had a pressing need for a very rapid computing engine, they managed to squeeze the digit period down to 3 microseconds, but could not get it to go faster. So although the Manchester and Ferranti machines had the random access property, you could not drive that form of storage faster, and it really one had to wait until the onset of ferrite core stores before workable, reliable random access memories came onto the scene. This little picture here is just one slice of what I've always thought is an elegant, almost iconic design for the pilot base, and you can see to this day, you can see that mainframe, so to speak, in the Science Museum. Here's a close-up of a long delay line. Here they are in the main photograph, where pulses were sent down a tube filled with mercury, reflected back, and you achieved this sort of 5-foot length as two smaller lengths. In comparison here, we have a nickel delay line store as developed by the Elliott Company. Nickel delay lines were more reliable and cheaper per bit than mercury-filled delay lines. They're also more reliable than cathode ray tube memories, but more expensive than the CRT store per bit. So to finish off with, what became of the pilot-based design, it was taken by the English Electric Company, who produced about 33 of these machines. I say about because experts have not entirely agreed on the exact number built. A successful machine, about a third of which ended up doing various engineering jobs within the English Electric Company itself. So that is the end for now of the NPL stream, and I'd like to hand over, if I may, to Martin, who's going to pick up the story, wind the clock back a little bit, and pick up the story from Cambridge. what we intend to do, and I'm so sorry that George Davis has been choking himself, but please forgive us, we're going to run on with these presentations and then have plenty of time for discussion at the end. Martin, over to you. Right. The Math Lab at Cambridge University was formed in 1937 by a theoretical chemist, Sir John Leonard Jones, and it was being used for theoretical chemistry and theoretical physics. At that time, they acquired a Meccano differential analyzer, a copy of the machine that was made in Manchester. And Maurice Wilkes, who's on the right in this picture, was at that time a research student in the physics of the atmosphere, this topic, had some differential equations to solve and started to use the machine. His enthusiasm was such that he became a real expert. And when Sir John Leonard Jones got funding to establish an actual computer laboratory, mathematical laboratory as it was then called, Maurice was appointed as the assistant director. Now, before the lab could really get going, they certainly acquired some desk calculators, various kinds of machines. The war started, and the laboratory was commandeered by the Ministry of Supply, and Wilkes went off to do war service, doing radar research and operations research, actually very good preparation for the world of computing. And he returned to Cambridge in October 1945, so a few months after the end of the war. And his mission then was to conduct research into computing and to supply a computing service to the university. Now, of course, he ends up building what is actually the first fully operational practical computer. And where did that design come from? And the answer is the EDVAC report. He was visited by L.J. Comrie in May 1946, who's shown on the right there. And Comrie was the proprietor of a commercial computing service called Scientific Computing Services in London. And he was helping Wilkes to equip the laboratory with calculating machines. Anyway, on this occasion, he brought with him a report he just received from the United States. Totally obscure then, very well known now. A first draft of a report on the EDVAC, the famous EDVAC report. And as Wilkes describes it, there were no Xerox copies in those days, so he stayed up late into the night reading it. A very impressive thing to have done if you've ever looked inside the EDVAC report. Imagining that you knew nothing about computers, how formidable diet of reading that would be. But as he said, he recognised it at once as being the real thing, and that the laboratory had to have one. His second introduction to this idea of the EDVAC computer came a few weeks later when he was invited to attend a lecture course at the Moore School of Electrical Engineering. The Moore School had recently, in February 1946, had publicly inaugurated the ENIAC computer, which of course was not a stored program computer, but it was the locus of where von Neumann was to make that invention. And Wilkes actually didn't arrive 6 weeks later for an 8-week course, but he didn't actually miss very much, because most of the first weeks were numerical analysis and electrical engineering, kind of basic stuff with which Wilkes was already quite familiar. So partly a degree of self-confidence that he didn't miss much, but also a degree of truth there. This is interesting, I think, because
these are not Maurice's lecture notes from the Moore School, but they are by a student who was with him there. And it shows you the things that were being talked about. So this is actually from a lecture on the left by Eckert, one of the co-inventors of the stored program with von Neumann. And you see here a diagram of the sort. It's not quite the classic diagram we're used to today, and you notice that the central processor, as we would call it, is called the computer. But it's actually, as far as I know, it's actually the first sort of diagram rather than a logical description of a computer. And you can see here the mercury delay lines are being talked about as a potential storage technology. Cathode ray tubes were also talked about at the same time. Towards the end of the course, which was mostly about numerical analysis and the ENIAC computer, which of course was the thing nobody wanted to build. And the students sort of formed a deputation and went to the organisers of the course and said, could you tell us about the EDVAC, because that's what we've come for, which hadn't got security clearance. So eventually, some sort of high-level negotiation took place, and they were allowed into a darkened room where slides such as the one on the top right were kind of projected onto a screen. And the students could make out of them what they would. It actually looks very familiar, that kind of diagram now, sort of decoding trees and sort of a register there somewhere. Anyway, so that's what Maurice learned. Anybody else who was at the machine, they could take away nothing apart from the notes they made while they were viewing those slides. And in September 1946, Maurice, coming back on the Queen Mary, started to sketch out a design for a machine he called the EDSAC. And he chose that name deliberately because it was very similar to EDVAC, the idea being that nobody should doubt the provenance of where the design was coming from. All of which you may say, well, what is Alan Turing doing on our postage stamps as the inventor of the computer? And there appears to be no connection. Well, the answer, I think, the evidence is really very little, much less than people are making out right at the present time. But what we do know is that Turing had visited Princeton University in the 1930s, that John von Neumann was extremely familiar with his work. Von Neumann was also had contacts with a pair of biologists called McCullough and Pitts, and in their writings they refer to Dr. Turing's ideas, actually without citing the 1936 paper. So there's a sense in which something may have been in the air around this time, so we'd be talking the late 30s, early years of the war. And really that's it. There isn't much more tangible evidence of that than that. There's no sort of smoking gun that would say, yes, the EDVAC computer is based on the Turing machine. Another feature that's often talked about is the fact that it's a universal computer. And of course that's one of the key ideas of Turing's paper. This is a phrase and a desire you never read about in the early computer literature. Nobody ever talks about it being a universal machine. At that time, remember the computer age hasn't arrived. And what they think they're building are scientific instruments. And they're building machines for doing mathematics. And that's really, so Turing has a terrific vision without a doubt, but it was not one that was sort of readily communicated to sort of engineers and down-to-earth mathematicians who are actually building these machines. Well, shortly after Wilkes got back to England from America in November 1946, about 2 months later, he's approached by John Wamsley, who was head of the NPL Mathematics Division, suggesting that they might jointly build a machine between Cambridge and the National Physical Laboratory. Maurice, surprising when you look at his correspondence from the period, he's actually quite sort of emollient really, and quite enthusiastic about the idea. And he makes a visit, and he sends them a report on what the EDSAC's going to be like. It's a 2-page report, but clearly the machine he's describing is an EDVAC type machine. He talks about serial operation and those things. Alan Turing is asked to comment on his paper, and it's useful actually to sort of take the measure of this. On the left is a diagram of the EDSAC, and if you could just cast your mind back to that picture of the EDVAC I showed you earlier, that diagram, they're remarkably similar. There's no question of the provenance of that machine. The one on the right is the diagram that Simon has shown you, and the machines are completely different. And Turing's idea is that the EDVAC design, in the EDVAC design, I guess we probably call it the von Neumann bottleneck or something nowadays, that pushing instructions for being decoded and then sort of sending them back would be inherently inefficient, and you didn't need to do it this way. So that's his design for the ace on the right. And as Simon says, it's an incredibly efficient design, probably in order, sort of in sort of computations for the pound, it's probably 10 times as cost effective as any other design. So it is a truly remarkable design. Well, Wilkes sends his proposal for the EDSAC computer, and Wansley shows it to Alan Turing, who was still at the NPL. And this is the report that Turing writes, and it's quite excoriating. He says, it's very contrary to the line of development here, much more in the American tradition of solving one's difficulties by means of much equipment rather than thought. It's an extraordinary condescending view of what Wilkes is trying to do. This correspondence, incidentally, was transcribed by Mike Woodger in 1977, and of course Wilkes never actually saw this report, but obviously sort of smoothed over the things. But anyway, they decided to sort of go their separate ways. When Wilkes saw this in 1977, he said he thought then, and he thinks now, that Turing was very opinionated. And what he was trying to do was completely at variance with what was going on at other centres. And you should always remember that Maurice Wilkes and Turing graduated in the same year, both in mathematics, both got first-class honours, they were both randoms. So these were people of very equal status. And Maurice felt there was not the slightest need to kowtow to Alan Turing. And as far as I know, he hadn't and maybe never did read Alan Turing's paper. But there's a bit more than this as well, because Maurice had a different vision of computing. Above all, he wanted to provide an operational service. And he thought the most straightforward way would be to take a trusted source, which he took to be the Law School of Electrical Engineering. He was an engineer at heart. And to sort of draw the lessons from what they were doing. The other thing he thought was that, now he doesn't say this at the time, he certainly says it retrospectively, that he thought that the mercury delay lines would be a transitional memory technology, that something would come along sooner or later, and perhaps quite quickly, that would be truly random access, and the whole concept of the ACE design would then be irrelevant. As he put it, if that new technology came along, it would be relatively straightforward to connect that new technology to the EDSAC because the memory was discrete from the main computer. That would never have been possible with the ACE design. view that Wilkes had was that he was going to provide a machine that was at least 1,000 times faster than any form of computation people had had before. And he thought that would open a whole new vista. So the idea of being 10 times faster again, he didn't think was particularly relevant. You're already getting 3 orders of magnitude improvement. Why would you want a 4th? And he also wanted to start experimenting in computer usage, which actually turned out to be programming. Well, the machine starts construction in late 1947. This is a picture from 1958. You can see Maurice is kneeling in front of the delay line store there, which is the technology he used because it was the only thing he could find around. He knew about the what was going on at Manchester, of course, but he had found a person at Cambridge who had come from the Admiralty Research Laboratories where they had been working on Mercury delay lines for echo cancellation. So he just took their design, he was given the parameters, and he copied them exactly. Again, it was a very sort of practical approach. The machine came to life on the 6th of May 1949, and there was an inaugural conference in June 1949, about 6 weeks later. And all the people in England and Europe were invited to attend. There were about 100 delegates altogether. And that sort of was the computing community there. Incidentally, Turing was there, and he did give a paper. Quite an interesting one. Wilkes wrote his first program, his sort of first program in anger, started in May 1949, just after the machine started working. And it was for the integration of Airy's differential equation, which was a problem he'd encountered in atmospheric physics. And he had an extraordinarily difficult time getting this program to work. And it's when debugging was discovered. It actually took him probably something like 20 goes to get this program of 100 instructions working. By a curious thing, he'd actually kept the original version of the program, which he showed me once. And there were 100 instructions and 20 of them were wrong. So he had discovered how difficult it was. So he decided to make the Cambridge mission, or at least it became Cambridge mission, was to sort of grab hold of the whole area of programming and make it their own. And I'm going to show you on this slide, actually, there are 3 styles of programming, which I think sort of show the difference in approach. On the left is the EDSAC program. This actually is the identical subroutine written for all 3 machines, so you're absolutely right. If you look at one on the left, it sort of looks, anyone who's familiar with an assembly language will sort of recognise that it's quite straightforward and looks. What in the middle actually is Turing's assembly language, well, machine code language, machine code for the Manchester computer. And how it works is that essentially it was a 20-bit instruction. So to write an instruction, you wrote down the corresponding teleprinter codes for the 4 times 5 bits for each instruction. So actually the written form of a program had absolutely no relationship to what the program was doing. Stanley Gill used to say he always thought Turing's programs reminded him of the Manchester weather. Because all these strokes look like rain on the window pane. And this is Turing's program, the Pilot Ace program. And what you have here is the program actually to go in 2 stages because of the complexity of the design. In order to get the speed out of the Ace, you actually needed to pack the instructions very carefully in exactly the right strategic position in order to maximise the speed. So he started off with a flow diagram, as I think they call it, which sort of describes the logic of it and the registers that you were going to use. But then you actually had to write this detailed code with all the timing instructions and so forth. Very difficult indeed to get working. Another point I always think is that if I was to put those on without the comments on, you could probably have a fair stab at what that program is doing. I don't think you could look at either of those or that one and guess what it was trying to do.
That's the unfair comparison. Flow chart. That means something by the time it's captured it.
This is, so Wilkes, after this experience of writing or doing the area integral, decides to give the job to David Wheeler, his research student, later becomes Professor of Computer Science at Cambridge. And Wheeler, people who knew him really rated David Wheeler as being truly the outstanding programmer of his generation. And this is the system he devised. It's sort of like, it's called the initial orders, but it's sort of like an assembler that you might have done in the 1950s. And the program, sort of written in its own code, of course, sits at the bottom of memory, and it reads in programs in a symbolic form from tape to tape. What was Wilkes' contribution to this? Well, partly recognising Wheeler's talent. He had extremely complementary talents. Wheeler was perhaps the least practical person in the laboratory, and Wilkes the most practical. So what Wilkes really set up was kind of a programming regime. So the subroutines for the programming system were kept in these little steel filing drawers, and there's people usually, this is post, people usually punch their own tapes. But basically the idea was you write your program and then insert subroutines from it. And all of the ideas of subroutines, incidentally, come from von Neumann and Goldstein in their reports from Princeton in 1948, except of course that the execution by Wheeler is very much more compact and elegant. Well, the second form of the initial orders, as they're called, sort of the new assembly system, comes into operation at the beginning of 1950, and it's from that point on that really serious computing starts getting done on the machine, and it becomes not just a system for use inside the laboratory by the denizens of the laboratory. The programming system is easy enough so that anybody else can use it. And Wilkes writes a report, September 1950, in which he details, lists lots of the subroutines and the initial orders and lots of programming examples, and sends it to everybody he knows in the world who is involved in programming, really trying to stake a claim for programming technology or a way of doing programming. Eventually that report finds its way to Addison Wesley, a publisher in the United States, and they published the report more or less exactly as it's written, except that they spell program with the little M-E. But otherwise, essentially the same document now comes as a book. And it sells something like 2,000 copies, which it's quite small beer by today's standards, but of course that meant that really every university had a copy, and everyone who was producing a computer at that time also owned a copy. So it really sets the stage for programming worldwide. So the whole notion of sort of using assembly programs really comes from here. So for example, it's used by IBM for the 701 series, and then kind of diffuses into the industry. Wilkes was surprised again around in the late 1970s when he discovered there was actually a Japanese computer that was based on the EDSAC. It had an identical order code. It's a transistorized machine built in the 1960s, but simply so that they could make use of the subroutines that David Wheeler had written in the back of Wilkes, Wheeler and Gill. And they had no contact whatever with Cambridge University. This came out of the blue. I think that's my go. Thank you.
Those of you who've seen anything to do with the story of Manchester computers know how complicated the story is over very many years. And today I only intend to look at a short span from the really beginnings in 1946 up to 1951. And you will know that the development of computers at the university and their transfer to Ferranti and then ICL continued for many years after that. Now, what I want to do, therefore, is try to relate Alan Turing's part in the work at Manchester and relate that to the other people there, in other words, his contemporaries there. And if we go back to 1946, this isn't quite how I designed this part of the presentation, but I shall therefore verbalise that we've already seen that the ACE report was delivered at the end of 1945, beginning of 1946, and that would have some influence or would be seen by Professor Newman, Max Newman, who was already at that point in 1946 Professor of Mathematics at the university, and who had an ambition to build or acquire a computer to do work on, to do research into mathematics, not for anything other than that. Here, Alan Turing was here at MPL, and Newman at Manchester, both mathematicians, and these two engineers, Williams and Kilburn, had decided that they could develop a random access memory using cathode ray tubes, using their experience in radar work at TRE, and had essentially been headhunted, or Williams had been headhunted to become the Professor of Electrotechnics at Manchester, and he was appointed at the beginning of 1947. They'd done some work on the memory system at TRE during 1946, and it was more or less working. It would store one single binary digit at the end of, towards the end of 1946, and they moved to Manchester to continue to develop the CRT store with the blessing of the Ministry of Supply. They would provide the parts from TRE and so on. Turing was still at NPL. Here. It's coming out entirely the wrong order, but there he was there. And in this time, as Simon has shown, Turing was really sort of developing a period of frustration, that he was inventing new designs and theory, but at NPL there was no practical work going on. They'd provided their lecture course in 46-47, and Kilburn was one of the delegates to that series, and I think he attended a couple of the lectures and came back saying, well, that's not how I'm going to build a computer. In other words, he was quite disenchanted with the idea of this kind of computer that Turing was looking for, and these engineers pressed on, making the store work by the end of 1947, and they recruited a colleague from TRE to come and help develop that memory and develop the baby computer to test the memory system. So we've got a picture here of work at Manchester, pressing on, doing something practical, with Turing still hanging about at NPL and not doing much and feeling frustrated. His contemporaries at Manchester were not all that inspired by Turing's ideas on how to make a computer, but nevertheless we mustn't forget that Newman was at Manchester, and Newman and Turing were friends and colleagues, and no doubt were in conversation continuously. I hope, and I'll point out here that the first program emerged in June 1948, a program running on the universal computer, and that really marks the first instance of a store program computer. Now, what was Turing doing? Turing during this time was frustrated, you saw earlier. In fact, interestingly enough, I can just see it very faintly. That's the trouble with these books. Turing well, let's see the baby. Those who haven't seen the picture. This is what the baby computer looked like, actually in late 1948. We haven't got any photos earlier than December 48, but this is more or less right. And you can see that the untidy racks of equipment, very much a small-scale experimental machine. And you can see the wires hanging over the top. The memory is in these three boxes here. This is the computer, and the operator's console is a set of push buttons and a monitor tube to peep inside the store. So the baby computer looked like that, but you know, don't denigrate it, it could actually run programs. So back to the script. Oh dear, this is nothing like right. Oh, I can see the problem, that it's all in faint, isn't it, here? Far too faint. Now, the next step is that Turing had taken leave of absence from NPL and went back to King's College in Cambridge to reflect on theory of computing and so on. And at this point, after the baby computer had made its first program work, the word got to Turing that it worked, and the order code was disclosed, and that presumably through Newman, who of course was on site in Manchester and knew what was going on. And Turing wrote to Williams in July and said, could I have details about this computer? Within a few days he produced a program, a long division routine. Now this is rather interesting. Here was Turing with his kind of obsession with his idea of how a computer should be built, using these memory tubes circulating in time. Yet nevertheless he was able to turn his mind round from that structure to the von Neumann structure that the baby machine had got, and within 2 or 3 days of receiving the order code, write a program, a routine to do long division. And it's rather interesting to look at some of the details of this. If you consider the long division by the standard processes, what were they can call. So quickly, we want to divide 989 by 43. How do we do it, pencil and paper? We say the quotient initially is 0 and the dividend is 989, and we subtract. First of all, we align the divisor so the most significant digits are aligned with each other, so we've shifted the divisor up. And now we keep subtracting, and every time we subtract we add 1 to the quotient, and then we try again, and we add another to the quotient, and it's still positive, the result is still positive, and we find that we've now got a new dividend which is aligned with the top, and we now have to shift the divisor down one place, and subtract again, and we add 1 to the quotient, and do it again, and do it again, and finally we've got the result 0. So we get the correct answer, 23, and note these matters, that the divisor has first of all been shifted up, and then it is shifted down bit by bit. There is a problem on the baby computer. It doesn't have any shift instructions. How can you do it? Well, you can shift up by doubling a number. You just add it to itself, and so you can shift it up, and that would take about 5 instructions typically to add, because the baby doesn't have an adder, it only has a subtractor. So to add, you've got to do repeated subtractions to get the signs right, and you can double that way. How can you shift down? That's a bit of a problem. And what Turing very cleverly did, and what I'm trying to point out is, Turing saw what the structure of the baby computer was able to turn his mind to the way it worked and so on in those 2 or 3 days, and he said, oh well, we can't shift down, we'll have to shift everything else up. So you shift up the dividend, and you shift up the quotient, and you have a little marker bit which at the end of the program tells you where it's got to. So here is the routine that you put into the computer, and it takes every one of the 32 lines of storage in the machine, and the various codes are down in the column there, and they're turned into binary and put bit by bit into the baby computer, and lo and behold, it will divide. It does a long division. Quite interesting, this is taken from Jeff Tutel's notebook, 10th of July 1948, only 3 weeks after the first programme, on the 21st of June 1948, and it says here, Turing long division, well, next one will be a bit short, Turing long division routine, proposed by A.M. Turing, the 9th of July, corrected version, in other words, it didn't work. Tutel corrected it. I think this is an amazing tour de force to get that routine exactly into 32 lines, the total storage of the computer. So Turing was quite bright, wasn't he? So back to the script here, the long division took place in July 48, and now the baby machine was going great guns. 3 more engineers were recruited to the team. Thomas and Edwards, postgraduates doing postgraduates in physics, and they moved into this department to do the work. Robinson had been working for at least a year developing a multiplier in a laboratory adjacent to the baby, and around about this time the multiplier was brought in and added to the baby, and these other people worked. So we've now got a team of 6 people: Williams, Kilburn, and Tutel and Robinson Edwards Thomas working on this machine. A heavy preponderance of engineers working on the machine, and they added all sorts of useful things like B registers and so on to the machine. Meanwhile, Turing had been recruited by Newman to join the mathematics laboratory at the mathematics department at Manchester, and so he severed his connection with NPL at the end of his period of leave, didn't go back, and came to join the Manchester team. What a come down. He was now forced, as it were, to utilise the architecture of the von Neumann architecture in the Manchester computer. But on the other hand, it gave him an opportunity to get hands on an actual computer, which was of interest to him. So what happened in the engineering side is that the baby computer was enhanced with all these various features, and a picture of it is here. And the team, all the team is here except for Tutel. We've got Di Edwards doing something, Williams peering at the monitor, Kilburn at his shoulder, Robinson looking at an oscilloscope, as is Tommy Thomas. And you can see right down in the bottom right-hand corner some bits of racks. They're the bits of the multiplier which had been brought in from the adjacent laboratory. And I think right down in the front here is the B tube, the index register. So essentially the prototype Mark I computer, which the university was trying to build, as it were, to provide the computer that Newman wanted, that prototype was the baby computer enhanced, and it's still got all the tramline wires over the top and so on. So it's a very hairy thing, but the engineers had been charged by the Ministry Supply, given and provided with the funds and encouragement to get Ferranti to build an engineered computer based on their prototype. And so these engineers at the university are busy building a prototype of a full-scale machine which would satisfy both the mathematicians and this requirement by government for a real computer. Now, to go back to the timing then, at least Turing now had his hands on a computer, and that he did. He would go and use the computer when the engineers were not enhancing it, and it now became apparent that the prototype was getting near to what was required for Ferranti to actually build a copy of it, and to do that, Tutel left the university and went to Ferranti, or he was sort of seconded and was to and from for 4 months at the end of 1949, carrying the know-how, the technology transfer from the university to Ferranti to build an engineered version of this. And during this time, the mathematicians, Newman and Turing, influenced the order code. So there was a design input to the Mark I from the mathematicians, in the sense of saying we want this kind of function. Strange functions like the sideways adder and a hardware random number generator, which frightens me to death because you could never debug a program, could you? And anyway, they put these designs in, and I think Turing is said to have contributed to the design of the input-output equipment, namely paper tape input and paper tape out, but I suspect that was more in terms of a requirement rather than doing the actual engineering. Then Robinson also went to Ferranti's as part of the technology transfer, so you can see the drift of engineers from the university to the engineering firm building this new computer. And that machine was completed and delivered to the university, the first one of the Ferranti Mark I's. That was delivered to the university in February 1951, and the prototype Mark I, that hairy thing we saw a moment ago, had more or less been abandoned by the autumn of 1950. So very interestingly, there's a hiatus of several months here where there was no computing facility at the university, and I do wonder what Turing and the others did in that time, rather than paper exercises. The Ferranti Mark I is now a much more beautiful thing in cabinets, but bear in mind that it's more or less the same structure as the University Mark I, but greatly enlarged with a big drum and big memory system and a proper console. And this picture shows on the left Brian Pollard, who was the manager of the computer department, now called the computer department in Ferranti's, and seated next to him Keith Lonsdale, the chief engineer of Ferranti's, and leaning on the desk, we believe, is Alan Turing himself. So the two engineers clearly are trying to get the machine working, and perhaps Turing is waiting for that to happen. So back to the story, we wrap up then with, now that there was a substantial engineered working machine there, Alan Turing wrote the programming manual, and that still exists and is what the original programmers were able to use, quite arcane. And lastly, there was the inauguration of the Ferranti Mark I at the university in, I think, June of 1951, and Turing got up and read a short paper, which really, when you read it, a defence of why he chose base 32 for the notation for programming, all these strokes and so on. But I must say, reading that paper, it wasn't very convincing of why he did it. That was the only really contribution that Turing made to this. What he did after that in relation to the people at Manchester leads to another story. Thank you.
Right, I'd like to spend just a few minutes talking about the work of Andrew Booth, who probably is the least well known today of the early British pioneers. His background was in crystallography. He was recruited at the end of the war by J.D. Bernal to automate the calculation, the solution of crystallographic equations. I'm going to have to go fairly fast. What I'd like to do is basically just briefly tell you the work of Booth from 1945 through to the early 50s, and then reflect just briefly on the influences on his work that we can detect, and make a few comments in relation to Turing. I am going to give a full version of the story of Booth's work to the CCS in Manchester in January. So if you happen to be in Manchester and you'd like a longer version of this, come along. Booth set out basically to build initially a relay computer, and here's a picture from December 1946 of Andrew Booth on the right, the lady who was his research assistant and became his wife, Kathleen Britton, now Kathleen Booth, on the left, and their research assistant in the middle. And this was simply a calculator. It had no memory. It was a very basic machine. And in 1946, Bernal, who was one of the major scientific figures of the time, obtained funding to send Booth briefly to the States to see what was going on in the area of automated calculations. He spent most of his time with von Neumann, who was a friend of Bernal's, and there is no question that von Neumann was probably the major influence on most of Booth's work. As a result of that visit, Booth worked on with his first version of the relay computer. Here is a very early picture from February 1947 of the relay computer that he built. I won't say more about it. It was a fully parallel machine, but sufficient for today. He had agreed in 1946 that the Rockefeller Foundation would give funding for him to go for 6 months in 1947. And again, he based himself with von Neumann, and he was given a copy of the von Neumann, so-called von Neumann report. He also met, and this is important for the direction of his own thinking, he met Julian Bigelow, who was working at that time on the various early developments on using a magnetic drum storage. And he wrote an interesting paper on bringing together his thoughts, together with those of his wife, on the physical characteristics of a computer. The ideas he explores for the actual implementation of the technology are in a sense his thinking. The actual structure of the machine is very much von Neumann. As a result of that visit, he then redesigned his relay computer into a von Neumann architecture. In order to do that, he now needed to add a memory. Just as a very brief aside for today, he brought back with him one of these office manager's voice recording machines, which used a paper disc, and he tried to use this paper disc as a storage device for the computer. I guess if it had worked, it would have been the first computer disk. The paper, when he spun it fast enough in order to be able to read and write data to it, it flapped, and in practice it was unworkable, so he gave that up, and then he moved on to the ideas that he, I think, had picked up from Bigelow, which was to use a drum. And he added a drum to his relay computer, and as far as I've been able to see so far, the ARC computer was the world's first machine to actually successfully use a rotating drum as its memory. And he reports May the 12th, 1948, the machine was, quotes, debugged completely. I think early machines were in practice never debugged completely. I think it probably meant at best it ran some small calculation. That machine did continue in use. It was adapted slightly, but it was still running in 1954. The drum, which you can see here in the picture, is reputedly in the store of the Science Museum here in London. I'm embarrassed to say, well, I've seen, and it was on display for many years, the small drum about the size of a cotton reel. I haven't actually ever seen the roughly 12-inch long drum, and indeed I must make sure that I do. He also, shortly after, produced the Booth multiplier. And the Booth multiplier, with a minor modification from a friend of his at Imperial College, is still used today in most of the ARM chips, for example, that are produced around the world. So if you have any sort of phone in your pocket, you almost certainly have a whole series of modified Booth multipliers sitting in your pocket today. However, we're not on that topic for now. He then decided in 1948, the end of 1948, that he would produce an all-electronic version of his relay computer. And he called this the simple electronic computer, and here is a picture of it being built, and this machine really was a sort of test bed for his ideas. It had come over basically from the ARC 2, the second version of his relay computer. It's just worth saying that the research student he had here was a guy called Norman and Norbert Kitts. I say simply in passing, he's an interesting man because if you Google him, you will discover that he was the designer of the world's first desktop electronic computer about 10 years later, Anita. However, we don't have time to pursue that either. SEC was completed, but I think was certainly never operational. It possibly never actually ran a program in anger. Booth was already working on an enhanced version of it, and he then produced two machines in succession, and these are the machines he's best remembered for, APERC here, and the other one, and its slightly bigger brother, which the second machine called APEX. The R reflected the fact that it was built and delivered for the British Rayon Research Association, hence the R for Rayon. They funded it, and it was delivered to them in 1951. It was built in a barn. If you see in the book, and you saw possibly as the byline on the title to this talk, it was built in a barn because Birkbeck was in the City of London. It had been burnt out of its buildings in the fire raids in 1941, and there was no space for banal, and even less for people who wanted to fill up basements with electronic equipment and so on. So he built it at home up in Fenny Compton in the Midlands, and he built it in a barn. And it was to that barn, here is Big Brother. This was a larger machine built a year or two later, APEX, and that was delivered to Banal's group for doing the X-ray calculations. The APERC machine, the first of those two machines, became the basis for the BTM ICT 1200 range of computers, the HEC range as BTM called them. The prototype of that machine, HEC 1, has miraculously survived, more or less intact, and is in store in Birmingham. And hopefully one day we'll get it to Bletchley Park and put it on display, but it sits quietly in the storeroom there. This machine was the result of BTM entering into an agreement with Booth. Booth acted as a consultant. He gave BTM his circuit diagrams from APERC. They in exchange gave him punch card equipment, card readers, card punches, and for a number of years he had a successful collaborative arrangement with them. The APERC machine was copied by Dickie Bird, who will be known to some of you, still alive and well, living in Berkshire. Dickie Bird went along in a freezing cold February in 1951, copied the circuits from Booth, and built this machine which was finished by the end of 1951 and worked either very late 1951, possibly 1952. That machine went on then to be developed through a series of evolutions with larger drums and faster processing, and initially it appeared as the HEC 2M, which was the first machines that BTM sold, and that was in 1955, 1956. And then the 1201 and 1202 machines were produced, and they sold in excess of 80 machines, and so they really were the first British mass-produced computer. BTM basically went for a slow, cheap machine because those were what fitted their customer base of basically tabulator users and so on. That was what those customers wanted. They wanted an enhanced and upgraded capability, and that fitted very well. And these machines also were sold around the world, and you find a number of countries, particularly in the old Empire, the Commonwealth, New Zealand, East Africa, the first machines into those countries were these ICT 1200s. So what were the key influences then on Booth? There is no question at all in my mind that his visit in 1947 particularly to Princeton and to von Neumann was clearly critical. He understood and used the von Neumann architecture. He looked at Bigelow's experimental work on the magnetic drum, brought that back and applied it. And although it's not part of our story today, he also met with Warren Weaver at the Rockefeller Foundation, who was the officer of the foundation who approved his grants, and who had become, in the just after the war, had become a great enthusiast for the idea that maybe computers could do natural language translation. He thought that it was rather like code breaking, that you could sort of match one with the other and do that natural language translation was a sort of mapping process. Booth understood fairly rapidly it wasn't, but spent in excess of 10 years working on natural language translation. If you ask the question, how much impact did Turing have on Booth, I think the answer one has to say it was probably rather limited. Booth was primarily an engineer. He had a good background in mathematics and so on, but you can't find a link. Couple of other observations. Douglas Hartree's book, which some of you may know, his book from 1949, Calculating Instruments and Machines, which reviewed the UK scene at that time, has only a very brief reference to ACE and a brief reference to Turing, basically only for extending the diagrammatic notations. Following year, he produced a second edition. Turing's 1936 paper appears only in additional references, which were added to the second edition of the book. Turing, of course, wrote very little. It was mainly Wilkinson and Woodger and others who actually told the story. So I think we can conclude that Turing probably had, and his work probably had limited impact on Booth. Booth, however, does say a couple of things about Turing. One is almost a throwaway because it's an incidental. I inherited, I was on the staff at Birkbeck for many years until I retired. I inherited a research grant that Booth wrote in late 1947. He writes the following. He's describing other projects that are around in late 1947. He doesn't mention Manchester at all. He does mention the Cambridge project, but of the NPL activity, he says, regarding ACE, as far as we can gather from a rather old technical report, and from more recent conversations with Dr. Turing, the order code is rather complex and more suited to the needs of mathematical logic than of the processes of arithmetic. he obviously knew about Turing's work, the design of ACE, but admittedly it's in a research report where you don't necessarily praise your competitors to the ceiling. Nonetheless, I think there is a sense here that he does not regard it as a major and central initiative. However, Booth is known, Dickie Bird, for example, who worked very closely with him, has a great respect for him as an engineer. And so when Booth says of the ACE is particularly well designed. It employs 1,000 valves and is compact in structure. This simplicity has resulted in a reliability of operation which is probably unequalled at the present time. That was he was saying in 1952. That, I think, is praise from one engineer to another designer of a computer. So, in summary then, Booth was certainly a natural engineer more than a mathematician. He tried the disk. He built the drum successfully. He pioneered natural language. He was the father, grandfather perhaps, of the UK's first mass-produced computer. And in particular, the thing that still stays today is he's the designer of the Booth multiplier. Thank you.
Thank you very much, Roger, and thank you very much indeed for my other collaborators, namely Martin and Chris. What I want to do for the last quarter of an hour is attempt an assessment of how Turing appeared to his contemporaries then, namely in the early 1950s, and then to bring the story up to date and explain why Turing has, in my view, grown in stature from the public imagination, at any rate, since those early days. So back in 1952, I want us first of all to think in terms of what the wider scientific community must have thought of Turing in 1952, and then we'll focus more closely on his computing colleagues in a little while. There's a list of all Turing's publications by 1952. I think all except one of those had been published. He's a mathematical logician. 7 of those 10 mathematical papers were published before 1945 and 3 after. Morphogenesis, which is a subject to do with embryology and the growth and form of living things, was an interest that Turing had from, in some ways, from an early age, but it came to fruition in his mind in the transition period that Chris talked about in Manchester, when there was a hiatus between the demise of the university prototype machine and the arrival of the Ferranti Mark I. And it was just towards the end of 1950 that Turing first, as it were, put pen to paper and started running on a desk calculator the differential equations that were at the foundation of his diffusion theory of embryology. At any rate, going back to Turing publications, if he were to apply for another job at that time, of course Turing would not have done, but he might have been asked to apply by somebody else, he would have been classed, as you can see, as a mathematical logician. I put in blue his computing papers because, frankly, these were modest publications by Turing standards. One was a single page and the other 2 pages. Chris has already mentioned that the second one was an attempt to justify using the teleprinter code. And this one was of more interest, but still it was a tabular checking mechanism and not perhaps what one might have expected from a person of such intellect as Turing. Now, focusing more on his computing colleagues, don't let the two blue papers fool you. Turing, when he came to write the first programming manual for the Ferranti Mark I, could at the drop of the hat descend or transcend into more formal methods. This is from page 8. Page 8 of a 109-page foolscap document, and we still haven't, by page 8, seen a single instruction from the computer. And here's Turing's sort of slide into finite state machine theory to describe how you move from one state to another as instructions are obeyed. On page 10, you do get the first tentative little program, this being multiplication by successive addition, and as Chris has said, it's hard to read that as a piece of code. What's interesting is the number of corrections in black ink, here 4 on this page. The manual did need a certain amount of correction. So that's Turing at the onset of the Ferranti Mark I at Manchester, and we've seen that he was already beginning to think of the morphogenesis application rather than think about computer design or indeed advances in computer programming systems. Here I'd like to summarize the rather sort of indistinct from a historical perspective, the indistinct last sort of 4 years of Turing's life at Manchester, when to an outsider one might imagine that he was involved in central computing activity, hard or soft, probably soft, but certainly to do with computers. Actually, what was in his mind was an application, morphogenesis. And here's a few sort of steps on the way until one arrives at the bottom at his tragic death in 1954. There are 2 or 3 names that I mentioned here that are relevant, to the computing world. Just excuse me while I get another sip of this gin. You'll see Chris Strachey's name mentioned up here. An interesting man, Christopher Strachey, who come to Manchester prepared to debug a drafts program. Turing took to Strachey and said, why don't you instead write an interpreter to simulate the machine, which Strachey did, ending up with a 1,000-line program, by far the biggest that was written for the machine in that stage, and he got it right in very little time. What's interesting to me is not so much that Christopher Strachey proved himself such an excellent programmer, but why wasn't it Turing who was interested in writing this emulator? Surely this would be the sort of thing one might expect Turing to have done. Similarly, when Alec Glennie, an ex-Cambridge person, comes up to use the computer in connection with atomic energy calculations, Alec Glennie worked for AWRE. In the summer of 1952, Alec Glennie developed his private autocode system, and you might think, well, surely Turing might have been interested in this sort of thing, but not a bit of it. Turing did, however, do some desk running, dry running of a chess algorithm with Alec Glennie. They seem to have hit it off together. Again, one might ask, why wasn't it Turing writing these chess programs? He was clearly interested in artificial intelligence. Some other events that happened during this time are on the more tragic side and would certainly explain the other pressures under which Turing operated. His house was burgled, the house at Wilmslow, south of Manchester, was burgled at that date, and that led in a fairly short time for Turing to be accused of and found guilty of gross indecency. and indeed obliged to undergo the horrendous experience of organotherapy treatment, which lasted a year. So clearly the poor chap had a lot to contend with. It did not, these tragic events did not stop his active mind beavering away, and he pressed on with the morphogenesis, took on a second research student here. The first research student Turing had taken on was Audrey Bates, who got a first in maths at Manchester. She started on an MSc project in the autumn of 1949 and finished it a year later. Her title of her thesis was on the mechanical solution of a problem in Church's lambda calculus. Audrey didn't pursue her studies to PhD level for at least one good reason, as she recounts, that in 3 months after she started, Max Newman, Professor Newman, said to her, "Well, Miss Bates, I don't think anybody will ever get a PhD in the subject of computing." So there we are. Audrey Bates took herself off to Ferranti and lived happily ever afterwards. The second research student was Bernard Richards, who was taken on to attack a particularly difficult sub-problem in morphogenesis, which he got a fair way to bring to a satisfactory conclusion. Bernard Richards is alive and kicking today, and I think he will talk at the Manchester conference in June, so if you want the full story there, talk to him. The impression I want to leave with you is, here is a man, a genius, yes, working in a hotbed of computing activity, which is Manchester at the time, but his thoughts were really elsewhere. What else was happening in Manchester? Well, the engineering group were busy. This is a picture of the experimental transistor computer that burst into life in November 1953. Believed to be probably the world's first transistorized computer, and the fellow Metfit took the design and re-engineered it and produced Metfit 950. A few months later, in May of '54, the prototype called Meg of the Ferranti Mercury burst into life. So there was a lot of computer design activity. None of it appeared to be interest Turing at that time. On the software side, Tony Brooker, R.A. Brooker, whose name I forgot to point out on the previous slide, he joined from Cambridge and taken over Alan Turing's job as being in charge of programming systems at Manchester. And by March of 1954, he released his Mark I autocode system for public use, and this is said by historians to be the first available high-level language. It solved, for the programmers of the day, it solved three problems. First and foremost, of course, writing your program in symbolic terms like this was rather easier than having to learn the teleprinter code. Secondly, it's a convenient way of calling upon standard library routines, a square root routine, for example, print routine. And thirdly, and floating point software. And thirdly, it provides a framework for the easy and almost transparent handling of data between two levels of store, the fast primary store, random access, and the drums. And at least one person in this room has described the autocode system as probably the most fundamental piece of software to have been produced in the mid-1950s. Again, one would have expected Turing to be at least interested in this, but he wasn't. I go back to saying he was not, because his mind was, one might hesitate perhaps to say obsessed with the problems of morphogenesis. This is Turing cut out and pasted to a single piece of paper outputs from his program to study offline. This collection is May 24th. I think it's 1953, but we can't be sure, at least I can't be sure. And you'll notice some comments. 3 steps, rather unconverging. How did this happen? And down the bottom is a hint that Turing had developed his own private scheme for kind of interacting with a program. This says ** action, what next? And was one of a repertoire of 4 or 5 such messages that could be printed out. And one may imagine Turing sitting at the console responding by typing in parameters, etc. So this is what was occupying the man. And it is no wonder, I think, that he regarded this as a much higher intellectual endeavour than building floating point hardware or grappling with transistors. I have to say, I think people today, we should be grateful for those who did grapple with floating point hardware and with autocodes, but for Turing, that was a lesser activity that he was content to leave to others. So that's the picture in the early 1950s. Now, what has happened since then and since his death, to Turing's reputation. And here I'm guessing, and maybe we can hear some comments from people who were alive in those intervening years who can comment. I think the influence of Turing's theoretical 1936 paper on computable numbers only gradually extended into theoretical computer science, partly because for the great run of laboratories and industry, there was very little computer software, system software, let alone the theory of software. And if you try to imagine at what point provability or computation theory came into the syllabus of undergraduate computer science courses, I don't think even by the mid-60s it had really got there. It was after that. A somewhat similar story with AI, artificial intelligence, that it was in the realm of philosophy to begin with, debated by philosophers, and intelligent machinery in the context thereof, the Turing test, didn't, I think, begin to impact on practical computer scientists until perhaps, the mid-60s. There were certainly isolated examples of checkers programs, the design of Lisp, etc. before that, but AI as a topic didn't, I think, gain momentum until some time later. Of course, Turing is today perhaps best known for his work at Bletchley Park, but in the 1950s and 1960s even, that was a secret world. And it was only in the mid-1970s that people like Brown Randall got to grips, and was allowed to get to grips with the design of the Colossus computer, and that gradually became public knowledge. I think a landmark in the progression of Turing from, as it were, obscure genius to national treasure probably was the appearance of Andrew Hodge's scholarly biography in 1983. And things have gained momentum ever since. You may recall that in 2009, the Prime Minister, Gordon Brown, apologised publicly for Turing's treatment in the sort of organo, whatever it is, therapy in 1953. And today we see ourselves in the middle of the Turing year, and clearly many Turing centenary events. I think I would like to end with pointing out the theme of our book, and also pointing out that there's lots to say on the counter of that, by saying that I think the message of our book is that in all the understandable celebration of the centenary of the birth of Alan Turing, it would be a pity if the celebrations obscured the memory of the real contribution of other folk in the late 40s and 1950s. Other folk such as Wilkinson, Kilburn, Wilkes, etc., etc. There are a lot of them, and without those people and similar groups in America and elsewhere, we would not have the computer that we have today. Thank you very much. We now have general questions. I think George Davis, who many of you know worked at NPL, has been bubbling over with enthusiasm. So maybe we let George Davis have it.
I'm slightly about making a contribution because I thought it was going to be all about Turing. A lot of other people came in, so the whole thing was totally frustrating. But I think Turing's contribution to actual computers was very limited. If he were taken out from history, National Physical Laboratory would have got a copy virtually of Cambridge NSAT, which was a much better machine for them to have, and much better computing because the combination of NPL's enormous computing power with what Cambridge would provide. So I think if Turing hadn't existed, actually on balance, progress of British computers would have been more. So I think that although I don't deny what the Secretary said, his position as a basic contributor to the start of computers, I don't think carries much weight. I'm not taking anything. Of all the very frustrating things that happened.
Thank you. Firstly, congratulations on the book. What I've read of it is splendid in many ways. I wondered if it's possible to say to what extent, if any, the people who were implementing computers, that's Turing, his contemporaries, including von Neumann, to what extent they were consciously and deliberately implementing any idea of a universal Turing machine. Or is it fair to say that actually the realization of the modern computer was driven from below by engineering? So the question is, to what extent was the universal Turing machine a conscious driver in the implementation by these various groups, the five of which you named, plus the AS group?
Well, if I may have a go first. Personally, I think that the main implementers were into providing a fast calculating machine. As Martin said, look at the way they were describing their computers. The word automatic, the word digital, the word high speed comes up. So I think the concept of universality, if it entered the minds of the engineers at all, it was really thought to be not relevant to the problem they were trying to solve, which was to provide a rapid and more general, easily used calculating engine.
My feeling is that it seems possible that von Neumann might have been influenced by Turing, at least he knew of the work. But after that, I think Turing kind of disappears in a way, because then the EDVAT report comes along, and whether that contains no citations. So even if it was influenced by Turing, we can only say it's pure conjecture at the moment. There's really no evidence of a tangible kind. And I think, as I said earlier, this idea of universality, I think that really comes later. Not for Turing, of course, but for most people, we're building mathematical instruments. And the von Neumann design, well, the EDVAC design, I think for them it was self-evidently a good general-purpose computer. I think it's no coincidence that Babbage comes up with an extremely similar design, or came up with an extremely similar design in terms of Victorian technology. The idea of the sort of the mill and the store, and the programmed instructions. The only distinguishing feature really is the idea of an internal program, and that, of course, is fundamental to the Turing conception, but it's not a particularly important part of the EDVAC. The fact that it can manipulate its own instructions, which would be the universal feature of the machine, which is where programming systems and lots of other things now come from. If you look at the EDVAC design, its real use actually is for manipulating matrices. There's no reference to doing anything grander than that. So it's really a way of sort of being able to address the von Neumann store. And once index registers come along, even that vanishes actually. So that's my take on it actually. That there's a heck of a lot of conjecture actually, and very little evidence.
Right. I very much agree with the general picture that's been presented, but I'd like to just deal with one trivial point and one rather more important point. The trivial point is that Turing was interested in morphogenesis from at least 1942. There's a very famous passage by Joan, the girl that he nearly married, about them lying on a bank. And, I won't go into details, but the idea that his mind, once he'd seen how to deal with a particular branch of mathematics, turned to other possible applications, seems to me very strong. I think he was bored with numerical analysis at NPL. But to the more fundamental point, this relationship between him and Alan Turing, it really was much closer than it seems to me has been presented here. John von Neumann came to Cambridge and encouraged Alan to go to the Advanced Studies Institute. While he was there, von Neumann acted as his boss, if you like, and offered him a post to build a machine at the end of his time, and of course Alan chose to return to Cambridge. During the war, John von Neumann was given absolute authority to look at all the computing projects that were being conducted by the, in inverted commas, allies. And indeed, in the States, he certainly did. And this was for the computing for the Manhattan Project. He came to England at that time, and I think almost certainly met Alan Turing. I think we know he came to Bletchley. My guess is that Alan wouldn't have been allowed to talk about any thoughts he might have had for the breaking of the fish codes at that time. But nevertheless, if the two of them did meet there, I find it very difficult to believe that he didn't once again renew his interest in Alan's thinking. It's well worthwhile trying to research that very small period while John von Neumann was in the UK with authority to look at all the computing projects.
David.
I, as usual, am going to be a bit of an outspoken in this issue. I essentially agree with what's been said. The shame to me is that the centenary of Turing, important though it is, important though Turing was, some relevance it had to the development of computing, has overshadowed a celebration of the history of computing. Now, fortunately, we haven't got the centenary of computing, so it's time to do it again and do it better. And I hope that whatever it is, the trouble is we can't define when computing began. I would hazard a guess of sometime late 1940s. So perhaps in 2040 something, we might have a proper celebration of the history of computing and see that really Turing was something of a distraction.
A thing that I caught, and which picks up on what Brian was saying about Turing being bored and going off onto other things, just right in the middle of Simon's list, it's something he never mentioned. Turing just addresses the zeta function, which I presume you mean the Riemann zeta function, which is the only extant problem of Hilbert's original 23. Not exactly a trivial matter. Another thing, I remember seeing a television programme a while ago about the Colossus saying it's Tut and Flowers who did that, not Turing. Is that true?
Well, thank you all very much indeed for this presentation, which was informative and entertaining, and what's more, there's a book. So that's absolutely splendid. So I just want also to remind you of what you've heard already about the Next Book 1 meeting on the 17th of May here, when Brian Carpenter from New Zealand will be coming to speak about ACE computers, so you might be particularly interested in that. But also our next meeting is on the 19th of April, when Dr. Ian Martin and Professor David Parsons will be coming to speak about centering the computer in the business of banking, Barclays Bank and technological change, 1954 to 1974. And British banks constituted an important early market for large-scale computing technology, and the seminar will explore how Barclays, which was Britain's biggest bank at the time, worked together with a number of different manufacturers to link its network of branches to its first computer centres by a variety of technological means. So that's going to be our next meeting on the 19th of April. So I hope to see you all then, and you can now buy your book and get it signed. And thank you very much for coming.